Hello, everyone. Welcome to GROOT. It's the first Wednesday series in the GROOT series. Today we've got Eleftherios talking about an introduction to rational homotopy theory.
Thank you. Well, thanks to the organizers, first and foremost, Julie and Willow and Zach, for having me as a speaker at the GROOT summer seminar this summer. And thanks to the students who are in attendance right now or watching the recording. Thanks for attending the talk. So the topic of today's talk, as the title reveals, is an introduction to rational homotopy theory. And before we get into that and kind of discuss the ideas and some of the constructions and give you a concrete example of the rational n-sphere, what takes place in rational homotopy theory, it's what I want to do first and foremost is I want to motivate, and maybe give a bit of historical context and explain how rational homotopy theory came to be. So the people in the audience might be familiar with the fact that, when you first learn about singular homology, say with integer coefficients, we have a lot of tools there. And one of those tools, for example, is the excision theorem. And another one of those tools is the Meyer-Vietoris theorem, which, for sensible decompositions, it gives you a long exact sequence in homology. And probably the first thing you do when you have Meyer-Vietoris is you compute the singular homology of the n-sphere by induction on the dimension n. Now, when you pass to another kind of invariant, homotopy groups, all of them being abelian from pi2 and above, unfortunately, you lose many of those tools. Now, you have a decomposition result in the form of Seifert-Van Kampen for pi1, but you lose any decomposition results for higher homotopy groups, and you don't have any excision for relative homotopy groups either. And this essentially makes your computations very hard, and maybe most notoriously so, the homotopy groups of spheres is something that, well, they have not been fully computed yet, and computing those things, which is kind of a sensible place to start, has motivated the development of many subfields of algebraic topology in the 20th century. And, if we were to list some of them, we would end up speaking about things like stable homotopy theory that came up in the last talk, and studying and computing the stable stems, the stable homotopy groups of spheres, and we will end up discussing all kinds of spectral sequences that are being used in practice. But the list would be remiss without mentioning rational homotopy theory, which is what I want to discuss today. So rational homotopy theory, the idea behind it is a very sensible one. You have those higher homotopy groups, they are abelian, but they're pretty hard to compute. And we see in the cases, like, for example, for spheres, that the torsion part can be quite complicated, surprising, counterintuitive. So you want to make your life a little bit simpler so you can maybe perform some kind of computation and get some information. A sensible thing to do if you have a bunch of difficult abelian groups to compute is why not tensor with Q, the divisible abelian group of the rational numbers, to kill the torsion and compute the torsion-free part of those abelian groups. But the way that you want to perform this tensoring, well, those are not just purely they're not just purely algebraic objects. Those are groups that have homotopical information. So you want to tensor with Q in a topological manner. And ideally, what you want to do is you want to have another space whose honest homotopy groups are the homotopy groups of the space you're studying tensored with Q. And you want this isomorphism to be induced by a continuous map from the space you're studying to that other space. So you want to tensor with Q in a way which is informed by topology. Now, because you want this to happen doesn't mean you can. But the topic of today's talk, what we're going to see, is that for all simply connected spaces, and I will say something about that, this is something you can actually do. Now, the theory extends beyond simply connected spaces to path connected spaces that might have a pi1, which is non-abelian, but it doesn't extend as simply as just ignoring non-abelian information. That's a separate topic that I'm not going to be addressing today. But all the spaces in the talk are going to be simply connected, so you only have abelian homotopical information from pi2 and above, and all the groups that I will be dealing with are going to be abelian groups. And kind of kick things off and begin, building this, this construction that I'm kind of promising you in this motivation part. Well, this theory is a topological analog of the theory of rational abelian groups and the rationalization of an abelian group, and it's done using this language. So let's begin with this as section one. Let's begin with rational abelian groups and the rationalization of an abelian group. And please let me know if you can't read or if there's any like accessibility issues so I can fix it. Now, section 1, right, talking about rational groups and rationalization, groups and rationalization. Well, first of all, I'm going to define what I mean by a rational abelian group, and I'm going to give a definition which is going to focus on the fact that I'm going to be thinking of those as abelian groups with an extra divisibility property in their definition. So, first and foremost, what is a rational abelian group? Well, an abelian group G is rational if for all non-zero integers, so for all k in Z, remove 0. Now you have this abelian group endomorphism given by multiplication by k, write it as m subscript k from G to G, which sends a little element to k times that thing. You ask for that to be an automorphism, i.e. to be an isomorphism from G to itself. Now, the way you should think of this, and I will elaborate on that later, you should think of this as being able to either divide by k or equivalently scalar multiply by 1 over k. So this rational name here, it alludes to rational vector spaces, and indeed the characterization you might be thinking of holds. So let me give you some examples and non-examples first and foremost that are going to be relevant. Well, first of all, 0 and q, well, qn in general, those are rational abelian groups. That's fairly straightforward. And also the direct sum of two rational abelian groups is again going to be rational. But now on to some non-examples and how this relates to like other types of abelian groups. I mentioned divisibility. Now, a rational abelian group, by this remark I made that this gives you division by 1 over k, it has to be divisible, but the converse need not be true. It's a stricter notion because you have, for example, q mod z. Now that's a divisible abelian group, but well, actually, it's torsion. And the way that this factors into the argument is that if you take, for example, the class of 1 over 2, and you look at multiplication by 2, that sits in the kernel. So multiplication by 2, for example, it can't be injected. So this is a divisible abelian group as a quotient of a divisible abelian group, but it's not rational. And since I mentioned torsion, let's see how this notion relates with being torsion-free. Well, every rational abelian group has to be torsion-free. You have a non-zero element of order k, it's going to sit in the kernel of this multiplication, so it's not going to be injected. But the converse is not true, because, for example, just take z, and that's an important example. We need to remember that z is not a rational abelian group. Well, there's two ways to see this. First of all, it's not divisible using the previous example. Another way is that multiplication by 2, it's going to be injective, but it's not going to be surjective. The image is going to be 2z, that's a proper subgroup. So here are some examples. Now, to write down the characterization that I mentioned before, and if you go on the schedule, I have uploaded notes where I'm kind of running those little arguments. So if there's any like questions along those lines, you can ask me after the talk, or you can have a look at the notes. But the result is that an abelian group G is rational, well, if and only if it has a rational vector space structure. Has a Q VS is vector space structure. Now, one implication from here to here, that's okay. Now, for the other implication, if it's rational, you define multiplication by 1 over k as the inverse of this map. So it's the remark that I made before. But I'd rather use this definition, first of all, to stress that I'm thinking of those things as abelian groups. And second of all, because it was quite convenient to explain those non-examples over here. Now, so we have the notion of a rational abelian group. The other thing that we need to discuss then is the notion of a rationalization. If I give you an abelian group which is not rational, Z for example, how can you associate with it in a more organic way a rational abelian group? And the way we do this is as follows. So it's this little observation that is right here at the bottom, that for every abelian group G, the way that you can get a rational abelian group from it, you just tensor over Z with Q. And a way you can see this is you can define scalar multiplication on simple tensors by doing the multiplication the second component, and that's well defined. It extends and it gives you a rational vector space structure on this. And therefore, using this observation, you can make the following definition of the rationalization of an abelian group. And in case you're a bit uneasy about, is this an arbitrary construction? I'm making some choices here. There's going to be a universal property that is going to make this a lot more canonical. So let's just write down the definition. So the rationalization of an abelian group G is defined to be the following abelian group homomorphism gamma G from G to this rational abelian group, which sends little g, well, to little g tensor 1. So there's nothing surprising about the formula. Now, a couple of examples. Well, first of all, if G is a torsion of the abelian group, for example, finite, then, well, the target is 0, so the map itself is 0. So if G is torsion, then, so this thing by no means has to be injective. Now, another example is if you take, for example, Z, and you identify Z tensor Q with Q, you have that gamma Z can be identified under this identification as the inclusion of Z in Q. And another example with regard to direct sums, if you do the identification of direct sum tensor being the direct sum of the tensors, under this identification, the rationalization of G plus H can be identified with rationalizing G, direct sum rationalizing H. Now, to give you the universal property that kind of justifies this definition, let me just write it down, and all the proofs are in my notes, and I can elaborate on them after the talk. So you have any abelian group G, you have the rationalization map here. It satisfies the following universal property that for every group homomorphism into a rational abelian group R, so this is rational, then there exists a unique Q-linear map. This is Q-linear, that's rational and that's rational, such that this diagram commutes. And what this tells you is that this rationalization is unique up to a canonical Q-linear isomorphism, and also a remark that I will be using later on. If you start out with a rational abelian group, and for some reason you decide to rationalize nonetheless, well, by the universal property, it follows that this gamma G is going to be a Q-linear isomorphism. That's going to be an identification that I will be using in this talk. So if G is rational, then the rationalization is a Q-linear isomorphism. So the map from G to G tensor over Z with Q is a Q-linear iso. Now, with this little crash course, I suppose, on rational abelian groups and this little theory, what we're going to do is we're going to have an analog of this theory in the world of spaces, and that analog will be formulated in this language. So this is like our blueprint and our dictionary for what we're about to do. So in section 2, well, let's talk about rational groups. Let's speak about rational spaces, and you will immediately see why I will be restricting, or think for the definition even to make sense, I will be restricting to simply connected space. The rational space. Now, even though for a rational abelian group, I had a straightforward definition, for rational spaces, what you would want to do is you would want to take an invariant of the space, which is an abelian group, and you would want to ask for it to be rational. But the problem is you have two competing invariants here. You have the higher homotopy groups, and I'm assuming the space is simply connected, as I said. And you have, however, the reduced homology groups. And I say reduced because if you take unreduced, then H naught is Z and you lose immediately. And reduced homology over with integer coefficients, I mean. So you have these two competing definitions, and you have this burden of choice. But there's a big theorem which says you don't have a burden of choice because those two conditions are equivalent. Let me just write this as a, you think you have a choice, but you really don't. So suppose, let X be, SC being simply connected, space pointed, because I'm going to discuss homotopy groups. Well, then the following are equivalent. Number one, for all K, the homotopy groups of K, the Kth homotopy group is rational. This is where simple connectedness kicks in for this to make sense. And for all K, you look at reduced homology of X with integer coefficients, that's an abelian group, is rational. And then, if such a space satisfies either one of these conditions, then you say that X is a rational space. Now we have a definition. First thing you do, think about some examples and some non-examples. So, first of all, we had this remark here about building new rational abelian groups from home. Well, I will just by the first characterization, the product of two rational spaces is rational, and by the second characterization, the wedge sum of two rational spaces is rational. But now, some examples of spaces an example of a space which is rational and kind of a silly one. Well, space is weakly contractible, then it's rational because 0 is a rational abelian group. And finding a more thought-provoking example is going to be what I'm going to give you in the next kind of subsection. So weakly contractible implies rational because look at the first condition. However, as a non-example, well, of course, for all n at least 2, well, Sn is not rational, and look at pi n of Sn, or you can look at the nth reduced homology. Both of them are Z, and Z is not rational. So now that we have some spaces which are rational, some spaces which aren't, let me give you an example, which is first of all a more interesting example of a rational space, and second of all, an example which is closely related to the failure of Sn to be rational. What I'm going to do is I'm going to include Sn in a bigger space, the so-called rational n-sphere, which is going to be rational. And that's going to be the example that I'm going to be touching base with throughout the talk. So we have, these examples. Well, let me just formulate it in the form of a question. So question, well, let n at least 2. So is there a simply connected space, going to be a CW complex by construction, which I will automatically denote as SNQ, the rational n-sphere, well, such that, and since I'm going to build it as a CW complex, I'm going to use reduced homology, such that the kth reduced homology of this space over Z, well, what's the next simplest example of a rational space? It would be a space that has reduced homology Q when K is equal to N and 0 otherwise. So that would be like a Moore space of type Q comma N. And at least in my head, this is the next simplest, in terms of homology, the next simplest example you should be seeking, well, after this one. So the reason why I took n to be at least 2, well, since I'm asking for a simply connected space, automatically by path connectedness, the reduced H0 is going to be 0, and because pi 1 is 0 by simple connectedness, so is H1 by the Hurewicz isomorphism. So you need this for the question to possibly have an affirmative answer. So let me answer my own question, and let me answer it affirmatively and by construction. So yes, let's build it. Build one. And actually, you're going to see that nobody can come and build a very different space from this one. There's going to be a universal property. Well, the way that you can build this, which is how I want to think about it, is using cellular homology and kind of working in reverse. So finding a chain complex that will give you this homology, and then reading from that chain complex the CW structure that you should put on that space. So what you want to use is, well, since you want to build Q as a homology group, you want to write it as a quotient. So you want to equivalently find an abelian group presentation for Q, and well, here is one, quite a natural one. You have the generating set of 1, a half, a third, subject to the relations. Well, 1 minus 2 times a half is equal to 1 minus 3 times a third. All of these are equal to 0. i.e., this corresponds, by the first isomorphism theorem, to writing Q as, well, this basis here will give you like the free abelian group on the natural numbers, and this relations would translate the following to the subgroup generated by 1 minus 2 and a bunch of zeros, 1, 0, minus 3 and a bunch of zeros, etc. So you have this presentation and it translates to this quotient description of Q. So now let's think what kind of a chain complex over Z would give me nth homology. This group over here, already written as a quotient, well, at 0, I'm going to have a Z, and then by reduced, it's going to go away, and 0 everywhere else. Well, such a chain complex would be, we could look as follows. We're going to have here the nth place, and minus first place, n plus first place, go all the way to 0. At 0, you're going to have a Z, a bunch of zeros afterwards. At n minus 1, you want to have a 0. You can put this thing here, so all of this is the kernel. And now you just have to find a map to this that has this as the image. Well, take the free abelian group on the natural numbers again, and we'll take the map that sends the kind of canonical Z basis to each one of the generators in that subgroup. So the first canonical basis element goes to 1 minus 2 and a bunch of zeros. The second one goes to 1, 0, minus 3 and a bunch of zeros, etc. And now, if you can find the CW complex whose, with a bunch of arrows here, you can find the CW complex whose cellular chain complex looks like that, well, then you win, because the homology of this chain complex is going to give you a Q, it's going to give you this quotient at the end place, it's going to give you a Z here, and then by reduction, it's going to go away. And notice that even if n was equal to 1, then, well, if n was equal to 1, you would be asking just for a path-connected space. But this, again, would be a chain complex that would give you first homology Q and reduce homology 0 everywhere else, because even if n was equal to 1, then the map from this to Z would be the 0 map for a cellular chain complex. So this computation also works if the case n is equal to 1. That case is called the infinite telescope, and that's why this construction is called the infinite telescope construction. So it's an important case, but not the one that I'm focusing on. So kind of to go back to the thing, get back on track. Well, let's read from this cellular chain complex what CW structure I need to realize this, to realize the cellular chain complex of a space. So how do I build the space reading this from the chain complex? Well, first of all, I'll have to erase this bit. And so this is what I meant by like working in reverse. That you kind of think.
Hey, Al, just to let you know, the board on the far left is the hardest to read.
Oh,
just for me personally. The other three are fine.
The board on the left. Is it because of like brightness or
maybe the other board's just closer to the camera?
Yeah, it's a little bit farther away, so it's a little bit more blurry on the left.
So
maybe write a little bit bigger on the left. Should be fine.
I'll write bigger. Thanks for telling me. So, all right, let's fix this. So how do let's work in reverse and read from the desired cellular chain complex the CW structure that we want. Well, what I read from this is 1, 0 cell. What I read from this is countably many n cells adjoined to it. So the n skeleton has to be a wedge of n spheres. of countably infinite wedge of n spheres, to which I'm going to join countably many n+1 cells, and the attaching maps, the degrees, are specified by what I want my homomorphism to be. And I mean, I can take them to be whatever they want by the Hopf degree theorem. So in kind of recap, the push out that would give me the rational n sphere, well, my n skeleton, as I said, is countable wedge. We'll maybe call this I. I'll use J for the other index. From I equals 0 to infinity, countable wedge of n spheres. And now I'm adjoining countably many n+1 cells. So here I have this joint union from J equals 0 to infinity of n spheres. That's the boundary of, well, the n+1 cells. The attaching map here, degree-wise, this is supposed to be an alpha, degree-wise, it's specified by what I want my homomorphism to be. Take the degree as appropriate. Hopf degree theorem says you can do that. So with an appropriate attaching map, you take the push out. Here you have the characteristic map. And what you get from this push out, from this gluing, is a space whose cellular chain complex will be what we want it to be. And that's the space that I'm denoting as the rational n sphere. So that's how you can explicitly construct as a CW complex this rational n sphere, which by reverse construction has this homology that you want. So first of all, it's rational. And I mean, second of all, it's not homotopy equivalent to the n sphere because, well, Q is not isomorphic to Z as an abelian group. So that's how you build it. A little bit of a remark is by cellular approximation, because the n-1 skeleton of this space is just the point, this space is not just simply connected, it's actually n-1 connected by cellular approximation. This is an n-1 connected space. And a little bit of another remark, and I'm explaining that kind of visually in the notes, so just put it as a remark, which we're not going to need, that if you do it for n is equal to 1, which as we saw, it's a sensible thing to do, this infinite telescope actually gives you an Eilenberg-MacLane space of type Q1. But the details, I'll postpone them to my notes. And if you have any questions, then send me an email anytime. So the case n is equal to 1 is actually important. It gives you a CW complex, like an explicitly built one, for an Eilenberg-MacLane space of type Q1. So now we have this example that we're touching base with. And notice, let me just write that over here, that you have an inclusion, say iota of Sn sitting inside this rational n sphere. And this inclusion is just under this enumeration of the wedge, take the first n sphere and it's sitting inside the rational n sphere. So you have this inclusion of this space, which is not rational, simply connected, but not rational, sitting inside a much bigger space, which is rational by construction. So you can ask yourself two things. First of all, an existence question. Can I do it for every simply connected space? Can I put it inside a bigger space, which is rational? And second of all, is there any universal property satisfied by this? Can somebody come to me and produce another such space, which is not even homotopy equivalent to this one? And to address these questions, well, we need to speak about the rationalization of a space, and that's going to be the next section of the talk. So let's automatically go to this board to make people's lives, well, easier. And let's start talking about the rationalization of a space. And to do that, I'm going to quickly recap and use the language of rational homotopy equivalences, which are supposed to be, and I will explain that they are, an even weaker notion of homotopy equivalence than weak homotopy equivalence, because what they're going to be is, well, weak homotopy equivalence is after you kill torsion. So without further ado, section 3, rationalization of a space. We spoke about rational spaces, and now the only remaining bit to translate from the theory of groups is the rationalization part. Rationalization of the space. And again, all spaces are simply connected in this talk. So let's begin by defining what a rational homotopy equivalence is. Well, a continuous pointed map between simply connected spaces from X to Y. is a rational homotopy equivalence. We'll abbreviate it like that because, well, life is a bit too short for this. It's a rational homotopy equivalence if, so for all n from 2 and above, you look at the induced map on homotopy groups, those are abelian groups, you can functorially tensor with Q to kill torsion. You get a Q linear map. So even only for all n at least 2, this Q linear map is a Q linear isomorphism. So that's what I meant when I said a weak homotopy equivalence after killing torsion. So now let's see how this relates and why it's a strictly weaker notion than the other notions of homotopy equivalence that you may have seen before. So if I have homotopy equivalence here, if I have weak homotopy equivalence here, and if I have rational homotopy equivalence here, first of all, let's see how I'm going to set this up. So every homotopy equivalence is a weak homotopy equivalence. That's okay to check. Every weak homotopy equivalence is a rational homotopy equivalence because if X star is an isomorphism, you functorially tensor with Q, you get another isomorphism. Now the converse implications under hypothesis are true, but under hypothesis. So a weak homotopy equivalence is a homotopy equivalence for CW complexes. That's Whitehead's theorem. So you need a pathological space to fail this converse implication, and I'll give you one. And every rational homotopy equivalence is a weak homotopy equivalence. For example, well, for rational spaces, because then tensoring by Q does nothing under the identification that I discussed in the first section. You know, you get an isomorphic Q vector space. So for rational spaces, the converse implication holds. But in general, those converse implications fail because, well, a weak homotopy equivalence, which is not a homotopy equivalence, I need to produce a space which is not even homotopy equivalent to a CW complex, so it's going to have to be pathological. Enter the Warsaw circle. That's never something you want to hear in a talk, but in any case, well, the map from the Warsaw circle to the point, it's a weak homotopy equivalence because all the homotopy groups of the Warsaw circle vanish, but it's not a homotopy equivalence because it's not contractible. And to fail this implication, a rational homotopy equivalence, which is not a weak homotopy equivalence, well, take, for example, any Eilenberg-MacLean space of type Z mod 2Z, 2. That's a simply connected space. It's not a rational space because Z mod 2Z is not a rational abelian group. It's going to be necessarily infinite dimensional because Eilenberg-MacLean spaces of like torsion groups, well, I think they have to be infinite dimensional, but in any case, that's some CW complex. You take the constant map, the map of the point, well, that's going to be a rational homotopy equivalent because after you tensor with Q, you get a bunch of 0 equals 0, but it's not a weak homotopy equivalence because, well, Z mod 2Z is not 0. So you see that under hypothesis, you can salvage the converse implication, but in general, this is a strictly weaker notion than this, and this is a strictly weaker notion than this. So we're kind of dropping information in the hopes of making our computations more doable. So now we're at this stage, and a result which connects rational homotopy equivalences with rational homology, by which I mean homology with coefficients in Q, is the Whitehead-Serre theorem. So, and I'm going to use that, we're going to use that to see that, well, the inclusion of the n-sphere in the rational n-sphere is going to be an example of a rationalization. So the Whitehead-Serre theorem says that if you have a continuous pointed map of simply connected pointed spaces, that this is a rational homotopy equivalence if and only if it's a rational homology isomorphism, i.e., for all K, you look at the induced map on rational homology, that's a Q linear map, from the rational homology of X to the rational homology of Y, if and only if this is an isomorphism, a Q linear isomorphism for every K. So this, along with that theorem over there and Horevich's theorem, they establish a pretty close link between homotopical information and homological information for spaces. And this is going to be something that I'm going to use like 5 minutes from now, because now that we have the language of rational homotopy equivalences set up, we can define what we want the rationalization of a space to be, and then I'm going to explain why such a thing why it exists. So it's not like an impossible definition. So let's see. Yep.
Would you be able to read the line above the diagram again? So the second line of the definition.
Oh, that one. Pi n of x, after you tensor over z with q, you have an isomorphism from this to pi n of y after you tensor over z with q. And this isomorphism is the induced map of f after you tensor with q. So that's, yeah, it got a bit messy here, but that's the definition. Does that make sense, or?
Yeah, that's perfect. Thanks.
Perfect. Thanks. So yeah, you got a bit smooshed there, but thanks for letting me know. So let me define what the rationalization of a space is. So definition, a rationalization of a space. So again, simply connected. Rationalization of a space X is, well, a map F from X to Y, where Y is rational, so it has a rational target, and, well, if you look at the homotopy groups, and of course, we're in a simply connected land, so we go for 2 or above. And now I'm going to use the universal property to phrase the condition. So if you look at the induced map by F on homotopy groups, higher homotopy groups. So for all in at least 2, here you have pi n of x, and F induces a map to pi n of y, F star. And that's an abelian group homomorphism with a rational abelian group as its target. So you can use the universal property of group theoretic rationalization to gamma to uniquely induce a Q-linear map that goes from the homotopy groups of X tensor with Q to the homotopy groups of Y. And I'm going to call this map F star because I'm going to be working just with this map from now on. So you can call this F star tilde or anything, you're never going to see it again. And you ask in the definition that this, for all n at least 2, be a Q-linear isomorphism. And now this is the precise formulation of the thing that I said we wanted to achieve in the motivation section, right? This is a Q-linear isomorphism between the homotopy groups of the space I'm studying with torsion killed to the honest homotopy groups of another space, and that isomorphism is realized, it is induced by a continuous map. So this is what I meant when I said you tensor in a way which is informed by topology. So if we can produce such a thing for every simply connected space, then that's exactly the goal that we set out to accomplish. I can take the homotopy groups of a simply connected space, kill their torsion, and identify them with the honest homotopy groups of another space, and the identification is induced by a continuous topological map because we're doing topology after all. So this is like the dream. Let's show that it can always be realized. So to see, first of all, the first thing that we would want to verify is that this inclusion here, well, it has a rational target, that this is an example of a rationalization. And the way you do this, you use the Whitehead-Serre theorem to characterize rationalizations in rational homology language. So proposition, and really follows from Whitehead-Serre, a continuous map with simply connected pointed spaces is a rationalization if and only if, well, first of all, you need the target to be rational. And second of all, by the Whitehead-Serre theorem, you can equivalently ask that this be a rational homology isomorphism. So for all k, look at the induced map by F on rational homology. That this be a Q-linear isomorphism. And then by a cellular computation, because this is by construction like a CW subcomplex inclusion, it's a cellular map. It's much more convenient to use this characterization to see that indeed, for all n at least 2, this inclusion of Sn in the rational n sphere is, as we have been alluding to, a rationalization. So now it remains to study the general situation and see, first of all, can I do this for every simply connected space? And second of all, is there some universal property to make this construction like unique up to homotopy equivalence? And the answer is yes. And the result is precisely stated as follows. Let's just go over here. And let's see, let's just address the general situation, an instance of which is the hands-on construction of the rational n sphere. So the big theorem says the following. Just write it over here. If I give you any simply connected space, like X, be a simply connected space, well, the first part is the existence. So there exists a relative CW complex well, such that the bigger space is rational. Actually, not just that, such that the inclusion of the space into this bigger space is a rationalization. And this subsumes what I said, that the larger space is rational. So this is an existence result. You can always stick a smaller simply connected space to a larger one by means of a relative CW complex, an example of which is that thing over there. So this generalizes very much. And second of all, you have a universal property that governs the uniqueness aspect, and it says the following. So here you have this inclusion, and it says probably what you would expect it to say. If you have any rational space sitting down here and a continuous map F, well, I need to be precise about to what degree it's unique. Well, first of all, I can put a map F bar here, and now to address the uniqueness question, every homotopy of maps from X to Y, so if this F can be homotope to a map G, that homotopy extends to a homotopy of the whatever map you can put here, to a homotopy from F bar to the corresponding G bar. So first of all, this map is unique up to homotopy for a fixed F. So F bar is unique, well, up to homotopy, and it technically depends only on the homotopy class of F, and only depends on the homotopy class of F. So in particular, let me just maybe border this from like the rest of the result. So in particular, like that. So we have that the rationalization of a space, and I can say the rationalization is unique up to homotopy equivalence, well, actually homotopy equivalence relative to X. If you change the universal property, you get that it's unique up to homotopy equivalence fixing throughout the smaller space that you're rationalizing. So indeed, somebody cannot come from like somewhere far away and give me a much different construction of a rational n sphere. It's going to be homotopy equivalent to what I built relative to Sn. And now using this theorem, I can define the rational homotopy type of a space. I can well define it as the weak homotopy type of the rationalization. So the rational homotopy type of a space X is the weak homotopy type of, and I can say de-rationalization, it's a well-defined notion by the universal property of x cubed. And what this is well, the weak homotopy type of x with the torsion kill, because that's what the homotopy groups of this rationalization are by the fact that this is a rationalization. So we can properly define the rational homotopy type of a space, the weak homotopy type with torsion kill. And so, for example, rational homotopy type of the n-sphere, the weak homotopy type of the rational n-sphere, or if a space has only torsion homotopy groups, then it has the rational homotopy type of a point. And rational homotopy theory, what it focuses on is studying properties of spaces which are invariants of rational homotopy type. So if you give a space that has the same rational homotopy type, then those properties are shared by those two spaces. So I think I have 5 minutes, is that correct? Or should I, because it's 12:49 here.
Guys, take up to 10 more if you'd like, but you can also leave time for questions. I think it's up to you.
I mean, I have a last quick remark that I can make, which is about the case of spheres. And, what about the rational homotopy groups of spheres? And what I want to say is that the rational homotopy groups of spheres were something that was known to, Sullivan and Quillen when they set this theory up in the 60s and 70s. And it's mostly the fact that they're fully known, and they were fully known back then, it actually provides like reassurance that indeed tensoring with Q and killing torsion can make your life simpler, because it's the case of spheres where we often see some weird torsion coming up and seeming fairly counterintuitive sometimes. So let me quickly address the case of the spheres. And the reason why the rational homotopy groups of spheres were known from the 50s is the following theorem of Sayre. Now, the homotopy groups of spheres below the diagonal, those were known even to Sayre, that pi I of Sn is 0 when I is less than n. That's singular approximation. Pi n of Sn being z, that's the Hopf degree theorem. What Sayre added to this in the 1950s, 51, is the following result, which says that, for the nasty case, which is above the diagonal, that's the one that's still haunting us to this day. So if you take I bigger than n, well then with one family of exceptions, pi I of Sn is finite abelian, and you have an entire family of exceptions, which is for even spheres, well, except pi of this family here, 4k minus 1 of S2k, where this is in general, you have a summand of z plus another finite abelian component, where this is finite. And now this f can be 0 or it can be bad. Some examples of both cases, if you just take k to be 1, well, pi 3 of S2, that is z, generated by the homotopy class of the Hopf vibration, so you don't have a finite bit. But if you take k is equal to be 4, you have pi 15 of S8, you have a z again, and that z is actually given by the homotopy class of the Hopf vibration associated with the opponents. But then you have a bit weirder summand of z mod 120z as well. So this f can be nothing or can be not the most predictable thing on the planet. And as a consequence of this, as a corollary, well, if you tensor with Q and you kill off this finite bit, you get that for I bigger than n, you can translate this to, well, pi I of Sn tensor with Q. Well, that just goes away, whatever it is. Well, except this family, F2k, where you tensor with Q, well, we just get Q. And a little observation that follows from this, and I will conclude with that. So if you go to the odd dimensional case where you don't have this family of exceptions, and you remember that the rational homotopy groups of spheres are the honest homotopy groups of the rational n sphere, you get the following consequence, that for odd dimensions, so for odd n, if you look at the rational n sphere, well, its honest homotopy groups are all 0 except the nth one, which is Q. So i.e., it's an Eilenberg-MacLane space of type Qn, and this vastly generalizes the case of n is equal to 1 that I mentioned in like the previous section. So for all odd dimensions, those rational n spheres that we kind of build hands-on as CW complexes, they're hands-on examples of Eilenberg-MacLane spaces of type Qn. So even though this theory was known, number one, it gives us some other nice results along the way. And number two, the fact that it indeed simplifies and makes computations possible in the case of spheres, that served as motivation, like in the next decade, for this entire theory to be developed, because it confirmed that, indeed, if I tensor with Q, I can do away with a lot of nastiness and actually get my hands on something. So this is motivation historically, and it gives you this nice result along the way. So, well, it's 54 past, and I shouldn't take up more time than allocated. So thanks for your attention. If you have any questions, then let me know.
So should we thank Eleftherios first? And yeah, any questions?
Thank you. I looked at the chat.
I had one question about this definition of rational homotopy type. It's kind of surprising to me that you take the weak homotopy type of XQ as opposed to allowing like all rational equivalences. So I guess there are more rational equivalences than just weak equivalences. So you could take this big collection of rational guys, but you don't. Any idea why not?
In my head, the reason why this seemed, when I was studying this stuff, the reason why this seemed like a sensible definition is because kind of along this theme of, rational homotopy groups, being homotopy groups of your space tensored with Q. Well, you take the weak homotopy type of the rationalization, then the homotopy groups that it consists of are precisely by its definition, like the homotopy groups of X tensor with Q. So basically this kind of fits along the general theme of, you want to think about the homotopy groups of a space without the torsion, and you want to study properties that preserve those things, the properties that preserve the weak homotopy type of X, forgetting the torsion. Now I haven't really thought about other competing definitions, or I haven't encountered any competing definitions, and I will definitely think about like this, the question that you asked me. Thank you for doing so. But that's kind of how I find it, like, that's why I find it intuitive, and I didn't like stumble or feel, I guess, uneasy when I saw the definition. Kind of fit in my head, at least, like the general theme of take the homotopy groups of a space and to simplify your the connected space, and to simplify your computation, tensor with Q. And this is precisely the information that this definition is like distilling. Does this help in any way, or?
Yeah, just some insight is very helpful. Yeah, thank you.
More questions? Oh, chat. Thanks, guys.
Well, I guess I have a question. So do you know about, so you have this theorem of existence of the rationalization. Do you know if there's like an explicit construction for this construction, like a rationalization?
I think so. So I'll have to send you to the notes for that one. I've added I didn't elaborate on the construction, but I've added a reference. Like the book that I used to learn this stuff was Felix Altohen and Thomas, the rational homotopy theory book. And there, it seems to be explicit. They seem to be constructing this CW complex. They seem to be constructing this space explicitly. So I want to say yes, but just to be sure, like I want to send you, I think it's most honest to like send you to the original reference, which might not be a satisfactory answer. But I mean, I have the reference in the notes if that helps. I'm pretty sure it's explicit, but I don't accurately remember right now. But
thanks.
Thank you.
There's another question in chat, which you may have just answered there about references.
Yeah. In the notes, there are notes on the schedule for GROOT, and there's references in the back, and they're cited along the way. And I also have a reference like chapter 13 of Griffiths and Morgan, which I haven't looked at yet, but it's a reference for those who are more familiar with like this theory and familiar maybe well beyond this talk for simply connected spaces and are now at the stage of thinking, how does it generalize to path connected but not simply connected spaces. So if you're at that stage, well, I have a reference that, you can go there and study the extension of that theory, but you're probably going to need a lot more than what the talk gives you to get there, to be honest. I don't want to make a false sell in any case, but there are references cited in the notes for what it's worth.
Did you run into anything that says whether or not this is possible at the level of spectra? Like, is there a rationalization, maybe like smashed with an Eilenberg or Moore spectrum or something?
That's going to be my question too. Yeah.
I haven't thought about this. I haven't studied it or thought about this yet, so I wouldn't be able to tell you. I have zero clue.
Okay.
But no, doing it like extending it at the level of spectra, that's a question I should have thought about when I was reading this stuff. Thanks for nudging me in that direction.
Probably there is a way to do it, but
I mean, you say yeah. More stuff?
Any other questions or? Sweet. So should we thank Elle again? Thanks for a wonderful talk. Yeah.
Thanks for having me.
And hopefully see you all on